Yeah, I think the answers in the back are not quite correct. I want to bring up the this Elmo unit so we can see what. Okay. Wait. All right. See, this is the box plots of ozone over the months January through December. And this represents January and so forth. Now, which was the C. Okay. Smallest range.
You look at the IQR and it's July is the smallest one.
Okay.
And but if they have like because the graph is shaped to the left, they have a one off there. Is that because the answer choose August?
I'm not. Okay, let me just, so the question was about C, right? Which month has the smallest range? By definition, the smallest range is the maximum minus the minimum. Okay, so in this case, you see, this would be the maximum and that would be the minimum. Whereas in this case, this would be the maximum and that would be the minimum. The minimum would be included in the outlier. Now, again, there's not as though there's a simple, fixed, absolute rule about what to do with outliers. What is an outlier? An outlier is some value that is somehow seems to be different from all the others. There is nothing magic about the computation of the upper fence or the lower fence. It's simply a rule that people have found useful. Like when the book says, add a dash, or the recipe says, add a dash of salt. I don't know, what is a dash of salt? Now, if you have access to the data in the original form, or you can actually go back and look at how the data was recorded, for outline values, you might want to go back and see if there wasn't a mistake. Somehow, in this case, was there a mistake in the instrumentation doing the reading? That might help clarify things. And whether or not it is real data, quote unquote, or whether there was a problem with the measurement system. But without any, I mean, you could reasonably say, you know, in this case, you see the range here would be this distance. I guess we don't need my glasses. This would be the range. Here we would include the outlier. If for some reason we could exclude the outlier, well then we wouldn't even do the analysis with it. We'd throw it out. We wouldn't have an outlier. We would say this was simply wrong. Now, if you look at the data in the original form that is on the Excel file, as I had one student in my other class do, he said, oh, there are some months that are missing. I didn't say this in class, but I'll say it here. Welcome to the real world. Data somehow, sometimes just disappears. You know, I mean, sometimes from, I think it was what, 26 or something to 1971. Folks, in 1971, they probably had some sort of, they probably had a charting device. They had computers back then, but I'm guessing they probably just had some of what, you know, you used to have little pieces of paper that would scroll by, and you'd have a little marker that would mark on the paper what the value that was being read. There was no way of recording data digitally. It was that long ago. I remember this era. So it could be, you know, a lot of things can go wrong. Even today, you know, your computer can have a glitch, your recording device can have a glitch, and your data goes away. So you exclude that from your analysis. Now, sometimes what you'd like to do is you'd like to have maybe the next best choice, maybe an estimate. Okay, sometimes you can come up with an alternative estimate, and that's a whole subject in itself. But the bottom line is, if you don't have data, you don't include that in the analysis. It makes the analysis more complicated, and surely that's the case in Excel, because if you have a cell that's missing, Excel doesn't like when data is not there. I mean, in some cases you can get around it, in some cases not. Yes?
So the IQR in the same question, the answer for number 2 would be the one with the largest green square.
Okay, yeah, it would be, now the question is, the largest one would be which of these?
Okay.
And so in my reading, this is definitely the largest. I think there's one problem. For example, the smallest IQR. I don't know, is it this, or that? I mean, you could whip out a ruler and try it that way, but yeah, you might, from the graph itself, you can't determine that. Now, this data, as is often the case for meteorological data, has a very nice pattern to it. It's what we call a sinusoidal pattern, or very close to it. If you had some trigonometry, there's something called a sine function. A sine function is a nice little wave. That's what appears to be the case here, and that's not surprising. If we were to take temperatures for these months, well, the highest temperatures wouldn't be in March, but it would be something like, maybe like that. It would be something like that. There'd be a nice wave-like pattern to it, a sinusoidal pattern. I mean, every year, January has about the same average temperature. February has about the same average temperature. This is very nice sinusoidal pattern to it. Now, when you look at this data, typically people would say, well, what was different about these years? Maybe there was something unique. Maybe this was particularly cool. I think ozone, let's see. It would, I mean, right off the top of my head, it would be, you know, ozone appears to be the largest one in the months where it's coldest. So maybe this was a particularly hot year. I mean, we could go back and look at what, you know, that value, and maybe look at the weather records. Was that a particularly hot year where somehow the ozone was very low? I don't know. And this is what people that are interested in meteorology do. They'll go back and look at the data. Is there an explanation for that outlier? Now, I don't know why this has the pattern, because I think, for example, in the LA area, the ozone goes up in the summer, and I'm not sure why they're different. There could be different dynamics taking place. This may have to do with the amount of moisture in the air. you know, life is complicated, and that's what this is what you do in science or engineering. Is you often look at the data and say, well, what's going on here? How do we make sense out of this kind of variation? Yes, in the back.
Can you go over or chapter 32 and chapter 4?
I certainly can. I was waiting for that one. Okay. In fact, I was so much waiting for it, I did it in the other class. So I think what we'll do here is I'm going to bring up the file that I created in that other class. Okay. Okay. So this is number 32 on page 75. All right. First of all, let's get over to the original data. So what I want to do is I want to look at those first two columns. Basically, this is the same data as in your text, except they, oh. That would probably help there. Okay. What is the meaning of this data? Well, one way of thinking about this is I have two individuals, both of whom have a measured height of 60 inches. I have 6 individuals who have a measured height of 61 inches, and so forth. Now, no one is ever exactly 60 inches or 61 inches. We can think of this too as representing the number of individuals who have a height between 59.5 inches and 60.5 inches. And it was rounded to 60 inches. Okay? Now, in part A, it says find the median and the IQR. Let's hold for that. Let's do B first. When I compute the mean, what do? I add all the heights together, and I divide by the total number of individuals in the group. Well, I don't have them listed singly. That is, rather than having 2 values of 60 followed by 6 values of 61 followed by 9 values of 62, which I actually sometimes have students do, another way of computing the mean would be the following. Let's take 2 times 60, that's 120. Let's take 6 times 61, I get 366, and so forth. Let's add all of those heights and then divide by the total number of singers we have, which is 130. And you get the same answer. We're using a fundamental principle of math. 60 plus 60 is in fact 60 times 2. It's an amazing thing what you learn in college, right? Have we done why we use a decimal system? We talked about this before? Count the number of fingers you have on both hands. That's why we use the decimal system. If we only had 8 fingers, then we'd use an octal system. All right. So basically, if you these cells here, this 320 is 5 times 64. So I take all of these values from here to here, add them together, and divide by the total number of individuals I have in the choir. Now, if you look at what I've done, see it says sum C2 through C18, which is right here, and then divide by 130. Okay. So that's how you go about computing the mean. What about the standard deviation? Well, in the computation of the variance, you would have in the numerator the following. You would have 60 minus 67.1. I'll just round it to 1 decimal place. That difference would be squared, and then I would repeat that for the next individual who has the same height. In other words, I'll have 2 terms of this form. I'm going to have 6 terms of the form 61 minus 67.1, that quantity squared. So again, what I can do is the following. I can replace this by 60 minus 67.1 squared times 2. And the next one would be 61 minus 67.1 squared times 6. Is that visible at all from? All right, sorry about that. The computation of the variance would be the following form. It would be 60 minus 67.1 squared plus 60 minus 67.1 squared, and so on. And then you divide that by 130 minus 1. This would be the same thing as 60 minus 67.1 squared times 2. I have 2 of the same thing. So if you look, I'll put this file on the website. What I've done here is as follows. The entry in this cell is computed by taking A2, which is right there. I subtract from it C19, which is the mean. That difference is squared. Squared is indicated in Excel by an up arrow, or what's sometimes called a caret, followed by a 2. And that thing is then multiplied by B2, which is the number of individuals who have a height of 60. Now, having set up the formula in this fashion, so the reference to C19 would not change because of the dollar sign, I could simply extend that down, which is what I did here. And then to get the variance, I take these numbers here, I sum them all together, and divide by 129. So if look at that, basically I'm summing all of these numbers here, E2 through E18, and I'm dividing by 129.
Why 129 by 130?
Well, the rule for the variance is you divide by n minus 1. Yes?
Isn't that called the sample variance?
Yeah, this is the sample variance.
The variance is just the number, you divide by the number. You just want the population variance?
No, the population variance you divide by n. So the sample variance you divide by n minus 1. We really haven't talked about the population variance. This gets back to what I said before. A difference is a difference only if it makes a difference. When you have a large number of values, whether you use what's called the sample variance or the population variance, it does not make much of a difference in your analysis. But we are going to use the sample variance in this class because it is more theoretically appropriate.
Can you show one more time the variance?
Okay. I'll post this on the so in my computations, you see I'm taking A2, which is right here. I'm subtracting from that C19, which is the mean. That's the mean right there. That difference is squared. An up arrow followed by a 2 means raise this quantity to the second power. And then you multiply that by the number of values you have. Namely, I have 2 values, both of which have a height of 60. I'll post this on the class webpage, all right, so you can see these formulas. Okay, now, how do I determine the standard deviation? Well, you just take the square root of that. The square root of 14.3819 is 3.79 and so forth. To compute the square root in Excel, one way of doing it is to use the function sqrt. You can also take a number and raise it to the 1/2 power or raise it to the 0.5 power, and that's the same thing. Okay, now, let's go back to part A. Part A asks you, in the problem I say, I give you instructions to ignore the part about the quartiles and the interquartile range, so I just want you to find the median in this case. The part, basically in part A, I want you to find the median. How do you find the median? Well, I have 130 individuals whose height is given here. Now, what I did here is the following. For part A, this number 2 represents simply this number here. The 8 represents the sum of 6 and 2. The 17 represents the sum of 9, 6, and 2. So this 17 means there were 17 individuals who had a height of 62 inches or less. 86 means there were 86 means there were 86 people who had a height of 68 or below. Now, I'll show you how I got that, but before I do that, let's figure out the median based on this information. I have 130 people. So how would I, if I had that list of numbers, how would I figure out the median? Suppose you have a list, smallest to largest, which positions do you want to know the heights? The middle two. I would want to know the height of the 65th individual and the 66th individual. See, 130, is an even number. So I take 130 divided by 2, and that's 65. And then one after that is 66. And the formula says take the 65th in the individual who was 65th in the list, add to it the height who is 66th in the list, and then divide by 2. Okay? Now, we don't have that list. But we do know what the height of the 65th and the 66th individual is. Well, there are 49 individuals who have a height of 65 inches or less. There are 67 who have a height of 66 or less. So the 65th individual and the 66th individual both apparently must have a height of 66 inches. There's a kind of, this is simply what we call a cumulative account, and this is a measurement of inches. But apparently the 65th individual and the 66th individual in my list, in my ordered list, both have a height of 66 inches. So, I add those two numbers together and divide by 2. And I get a median value of 66. All right, now, how do I get this list here? Well, you can do it by hand. Okay? Remember, back in the good old days, when we had these mechanical calculators, well, actually, I mean, when I was a student, you just had to get good at doing these calculations by hand. Okay? There's an easier way.
So you get a median of 66 because
Okay. There are 130 individuals. So if I think of my smallest value on the left and my largest value on the right, I have 130 values. So I have an even number of values. So to find the median, I would take the 65th individual and the 66th individual in my list, take their heights, add them together, and divide by 2. Okay, now, what is the height of the 65th and the 66th individual? Well, because 49 have heights of 67 or below, and 67 have heights of 66 or below, the 65th and the 66th individual both have a height of 66 inches.
Coincidence.
It's a coincidence, yeah, that 66 is the same as the inches is the same as the 66th individual.
Oh, I see.
Okay? It might be helpful, and I've done this in other classes, is convert these into centimeters. Okay? Let me do that. To find the height of an individual in centimeters, given that it's given in inches, you multiply by 2.54. Okay? So, if you have a measured height of 60 inches, then the measured height in centimeters would be 152.4. Okay? Now, so if I'm going to compute the median of the heights using centimeters, I want the 65th and the 66th individuals, both of whom have a height of 167.6 centimeters. Both have the same height. I add these two values together, divide by 2, I get the same thing, and I convert it back into inches, I get 66.
Why did you do the centimeters?
I'm sorry, what?
Why did you convert to centimeters?
Just to illustrate how, see, the 66 represents not only the height in inches, it's also the position in the list. This way we get away from having heights, or we get away from having 66. Anyway, 13 students. I don't know, I suspect this is real data, and sometimes real data is confusing. You have these oddities where 66 not only represents a height in inches, it represents what position in your list you want. Okay, now, so that's how you can figure out the median. How do you sketch a histogram in this case? Well, basically what you want to do is the following. This is your frequency. What is a histogram? A histogram is basically a graph of a frequency distribution. This count is also known as a frequency. So above 60, I want to create a bar of height 2. Above 61, I want to create a bar of height 6, and so forth. Well, I can do that in Excel by using a bar chart. Create a bar chart. And if I do so, I end up with this right here. Yes?
If we wanted to have fewer bars,
Oh,
would a reasonable way of doing that be like take 61 and group both 60 and 61 into that bin?
yes, you can group the 60 and the 61 together, and that's probably a better choice.
So would you then call it 61 on the bottom, or would you call it 65?
Okay, this represents 59. The low value here is 59.5, and the upper value here is 61.5. So I take those two numbers and average them, and I think that turns out to be 60.5. I think if you group these two bins together, you see these represent bins, all right? And I have, so think of this again as representing between 59.5 and 60.5. So I have two individuals in that bin. If I combine 60 and 61 into a single bin, then the range is from 59.5 to 61.5, and the average then would be 60.5. Okay?
That's what I would name that.
Yeah, so I would name that as the average of the 60 and 61. See, average of 60 and 61 would be 60.5.
You're never going to create bins out of bins. You're going to re-bin the entire original data set.
Well,
So you'd be creating your bins larger, but you'd be using the original data to do it.
well, sometimes you don't have the original data. Sometimes what you do is you make a good approximation. The question here is, anytime you collect data, well, let's go back. there are some people who actually collect and analyze data solely for the pure intellectual joy of doing it. These people are known as scientists or statisticians. That's how they get their kicks in life. Now, generally speaking, when people collect data outside that, they do so because someone is paying them, or there are consequences, there are financial consequences to this. So when people pay others to do statistical analysis, they're trying to get some information out of this that will help them make some sort of decision. I suspect this is probably real data. Someone had a choir someplace. They were probably going to purchase robes. Robes are probably ordered by height. So what do? You measure everyone's height. And this probably found its way to these three statisticians, and they said, voila! You know? We found some real data. But as a general rule, the question becomes, what do we want to do with it? In this case, I mean, I don't know how, measurements can vary over time. I mean, it could be that this choir actually was ordering robes, and they were ordering it to a single inch. That might be a little expensive because typically, you might want to have a greater range. In other words, rather than having robes of height 60 and 61, maybe there's just a robe of height 62 and 64, maybe even in increments of greater increments. All right? I mean, men's pants usually range the less expensive ones over 2 inches. I think isn't that when you buy, so you go from, they go in increments of 30 to 2 inches. For example, if you have an inseam of 30, the next one is 32, all right, and the next one is 34. There's some of us who are cursed to be right in the center. So the 30 is too small and the 32 is too large. There are other problems as well when you get married, but that's an issue. So, again, I don't know why the data was collected. And I suspect it's kind of interesting data. But you might want to rebin these, even though you are losing information. That may or may not be a problem. Depends upon what we're trying to do.
Chapter 5, number 11, which is page 101.
Okay.
My parking lot looks a little different. The southwest state.
Okay, hold on. Let me get to chapter 5. And which problem again?
Number 11.
Number 11. Okay. That had to do with population growth. Well, did I do stem and leaf plots last time?
No.
No? Okay. I think what we ought to do is hold on that, and I can help you either during break or after class. Okay? We need to talk about stem and leaf plots first. Okay? All right. What I'm going to do up here is I'm going to make a list of things we need to cover that I didn't last time. Make sure that I do in fact cover that. So we need to talk about stem and leaf plots. Did I talk about dot plots last time? No. Okay, so we'll put down dot plots. All right, let's take a look at my overheads here. all right, so we didn't have dot plots. We're going to talk about dot plots today. We'll talk about stem and leaf plots. I did histograms last time. Is that we did neck sizes and we did a frequency distribution? Okay. Now, let me point something out here. Because the data for the choir, the heights of the choir members, because that's already been, you cannot use the data analysis toolkit to create a histogram. Okay? You can't use the average function. You can't use the variance function. And that's because when you see 60 followed by a 2, it means you have 2 copies of 60. And so the data is not in raw form. Now what you could do, as I indicated before, is you could create a list with 2 values of 60. I think there were 6 people with 61, 6 values of 61, and so forth. And then from that, use the data analysis toolkit to create a histogram. That will work as well.
Do you mind if the answers to our questions have some handwritten and some Excel?
No.
Would you rather it be all in one?
No.
Okay, because it's easy to draw histograms.
Yeah.
It's almost easier to just
Yeah.
draw.
I mean, it's not. I'm interested in whether or not you understand the idea. Okay. I use Excel because that's the easiest in class. I think it's the most. But and if I were doing these homework problems myself, I often sometimes switch. In fact, when I make up keys, I often switch to say, let's just do it by hand. So I'm interested, do you understand what's going on? That's what I'm looking for. All right. Let's see. We've talked about, did we go, I think we got this far. Is that correct? And we've talked about the mean and the median. We've talked about the quartiles. We talked about, did we talk about percentiles? Did we say, for example, if you take a standardized test and you get a score back, and usually they also tell you a percentile, is that not right? Anyone take the SAT recently? Well, I took the SAT. I think they do it online these days, is that right? No. We had these little things I guess filled out. It was so long ago, I don't remember exactly how it was. All right? But anyway, what you did is you got sent in, and probably about 6 weeks later, you got the result back, and then they sent you a score, and then they sent you a percentile. The percentile means that percentage of students got that score or lower. So if you were in the 75th percentile, that means 75% of people taking that exam got that score or lower. If you got 91 or 95 percentile or 99 percentile, then you submit your application to Harvard or Yale or whatever, assuming you have matching grades. And that means you scored above the 99% of the people, which means that you are entitled then to the 1% club, where you get lots of money, right? Oh, sorry, I'm getting cynical. All right. So I think we talked about that the first quartile is the same thing as the 25th percentile. We talked about the variance, or more specifically the sample variance. Usually it's the context that determines whether or not we're talking about the sample variance. Or there's another thing which we might call the population variance or the theoretical variance. It's the context that determines which one we're talking about. When we're talking about data, we're always talking about sample values. Remember, a 5-number summary is not the data itself. If you have a 5-number summary, that may be based on 100 values, 1,000 values, or 25 values. Outliers. Outliers are numbers that are different somehow in some way. And the question is why? Sometimes you can answer that question and sometimes you cannot. Did we talk about resistance? Okay. Let's go back to the prior data here. Suppose I have a basketball player in the choir, and let's see, he comes in at 81 inches, okay? If I have a member of this choir who has a height, suppose rather than, this was misrecorded, this was, say, 81. Would the 81 change the value of the median? No. It would change the value of the mean because every value is used in determining the mean. The median, however, all that you do is you put the numbers in order till you find where the center is. It is not influenced by outliers. That's both a good thing sometimes and maybe a bad thing. When the nice thing about the median is it's resistant to outliers. That is, outlying values don't influence the result of the median. Sometimes that's what you want. In contrast, the mean is heavily influenced by outlying values. Every value counts in the mean. Every value counts in the variance. An outlying value can significantly skew both or change the mean or the variance. That's why you're looking for values that have an unusual impact on what you're trying to do. That may or may not want, you may want to include that in your analysis or may not. Whereas the median and the interquartile range, both of those are resistant to the outliers. They're not going to be influenced by those extreme values as a rule.
What would we call the opposite of resistant?
Non-resistant?
Okay.
I'm not sure I know of a term. I'm sorry? Resistant line? I'm not familiar with that term right offhand. If you want to find it, I'll take a look at it. Okay. Did we talk about which statistics should be used in describing data? Okay. Let's go back to one of the previous overheads here. All right, this is a histogram, which is roughly symmetric and unimodal. Unimodal means one peak. That's bimodal, there are two. Now let's compare these two histograms here. When we have symmetric data, unimodal symmetric data, usually if we want to describe the center, we'll use the mean to describe the center. And we'll use the standard deviation as a measure of the spread. On the other hand, if we have data which is skewed to the left, or for that matter skewed to the right, it's more natural to use the median and the interquartile range. And it doesn't mean you can't use both. It just means that if you're going to describe the center in a case like this, we'll use the mean and the standard deviation. Whereas if we have data that looks like either this or that, we would describe the center by the median and the spread by the interquartile range. It doesn't mean you can't use both. It just means there's a more natural choice.
So you're trying to find the way to describe the peak.
Okay. The mean and the median are both what we call measures of central tendency. When we give a measure of central tendency, what we're trying to do is describe where the center of the data is. Okay? If we have data that looks like this, it's usually considered better to use the mean to describe the center. In a case like this, because of this skewing, the effect of these values on the left, it's generally considered better to use the median.
So if you're using the median, which part of that would it be describing? Just the middle?
Oh, the middle. Okay, that's actually an excellent question. I'm going to go back to the choir histogram in just a moment. Okay, that will actually better address that question. Now, the other thing here is the following. When we have symmetric data, it turns out that the median and the mean are usually pretty close together. Okay? In this case, the median and the mean would be much different. And we would more likely use the median to describe the center. It's not as though, you know, we're more like in a cooking class here. You add a dash of this or a dash of that. When we get to more formal methods of inference, we almost always use the mean and the standard deviation. Okay? Most of statistical theory, not all of it, is based on normal models where we use the mean and the standard deviation. And that's also part of the limitations of our traditional statistics. So the thing is, I want you to remember we're trying to find ways of describing data. The center is sometimes described by the mean and sometimes is described by the median. If you see, now often what they do, this is the really kind of horrifying part. Sometimes people will use the word mean, M-E-A-N, when they mean median. Okay? And unfortunately, I think that's part of the confusion has to do with the fact that when you have symmetric data, the median and the mean are the same. In theory, you know, what's called a normal distribution, we didn't talk about normal models last time. No. Okay. In theory, for the normal model, the median and the mean are exactly the same. But when you have skewed data, the median and the mean are not the same. And in everyday usage of the word average or sometimes mean, M-E-A-N, they have different meanings than we do in statistics. Because when they took their stat classes, they weren't paying attention. Let that be a lesson to you.
Ooh, the finger.
Sorry. The evil eye, yeah.
Oh, nothing anymore.
Yeah, okay. All right. Now, so when a question asks you, how would you best describe the data? That's what they're looking for. Do you want to use the mean and the standard deviation, which is appropriate when you have something like this, or do you want to use the median and the interquartile range? Typically, well, the choir, let's see, the next sizes, when we did that histogram, it looked relatively symmetric. That seems pretty reasonable to me. When we have economic data, it's often skewed. I mean, income, assets, all that sort of stuff. skewed to the right. You know, when you throw in Bill Gates is over in the next county on this list. He skews it to the right. He's an outlier, all right, but it's real data too. All right. Okay. I think what we ought to do, we ought to take a break, and when we come back, I'll look at these two topics. And I think then, have I shown you examples of graphics? Did we show the Napoleon? Okay, I'll go over that briefly again. But okay, so let's take a break for about 10 minutes, and we'll come back and do these two topics. Two through five, yeah, probably, yeah. You could, yeah. Okay. Okay. I'm gonna have you sit out here. You wanna, yeah, I can't, yeah, or you can, I don't know. Okay, well, there's really, I don't think the test is that hard. Okay, the quiz is that hard. And you may, if you wish, I'm going to give the class a thought. Yeah, at the end, that's what I'm going to do at the end of the class. So, if you take more than that, it's fine. I'm sorry, why don't you come, I'm a little hard to hear. Okay, if. Oh, I see. Okay. This is what I recommend. Okay. Once I get done with that,
I told you, and I'm like,
yeah, it's going to be, we're going to spend a long time on this. It's up to you, but I think it would be better. I don't mind staying longer than half an hour. Again, I don't think. Just so you're aware, covering chapter 6. Okay, so if you're taking the quiz along with chapter 6, you'll miss out on. I don't think that's a good idea, but it's your choice.
So chapter 6 is going to be on the quiz?
No, not on the quiz, but it will be on the exam. Okay, and chapter 6 is. It depends on how good you are in math. Okay, so if you want to take it now, I'll have you go down to the computer lab and bring it back. If you want to do it now.
So wait, you're doing chapter 6 right now?
Well, after I get done with these topics. So it's gonna be probably about a half hour on this, and then we'll get to 6. We're gonna spend a long time at 6.
Okay.
Oh, okay. Let me get my glasses. Oh, okay. Yeah, probably, yeah. Well, back in the good old days. Yeah. Oh, yeah. Yeah, I think the intention of the author was to do that by hand. What you can do, I mean, you could enter this in Excel and ask it to sort. Okay, that's just enter the numbers in a column and then use the sort facility in Excel. Okay. Yeah.
For 2.
Probably maybe the thing to do is go to another, okay, this is your,
Or maybe put a note in here.
yeah. All right,
Right, so just don't just use that number.
Okay.
Usually if you write
Yeah, I'm sorry. Yeah. I would like accessibility and quality.
the good thing you're a young woman yet, because I don't think I'm running higher than that. Without having. Okay, let's try it again.
Yes, that's exactly what I'm saying, yeah.
Can you look with someone else?
Yeah.
You know, kind of,
So like,
I'm not sure I'm going to do that. I'll do a little bit with Excel. cables are exposed and someone kicks it, you may break the connection. Right. Yeah, unbiased, yeah.
And then they said, well, once you square root and you square root function,
Yeah. First of all, unbiased has to do with a probability and distribution function. Okay. Do you know it? Have you had calculus before? Oh, I see. There's something called an expected value. Which is a probability weighted calculation. The expected value of the sample variance is in fact equal to the, I guess we would call it the variance of the distribution. Okay. This is important in theory, and it has to do with probabilities and distribution functions, things like that. So it's a theoretical concept. And once you, the problem has to do with the